Now, in case of a PID controller, so as I told you that it is termed as proportional integral derivative, it's the abbreviation. And the benefit with this type of control is that it is quite robust, it's simple, and it's versatile. So you can apply, you can use this controller at multiple places where you will require. So I'll give you today some few examples related to PID control, and the mathematical or the quantitative study will be dealt with tomorrow in the next class. The drawback with this type of controller is that it controls up to only second order system. So this is one of the drawback. For higher order system, you cannot utilize PID controllers. So you have different controllers that you are going to use for higher order systems. Now, in order to explain that how PID works, so I am going to give you a few examples. One of which is the you might have heard about the which is this is we are going to talk about an anti-ballistic missile, in short abbreviated as ABM. So because we have a part in defense, our so in fact an ABM is a surface to air missile designed to counterbalance or counter ballistic missiles, which is used in missile defense. So in fact, this type of ABM or the anti-ballistic missile that fires a targeted missile. So before talking about that specific case, let us first try to understand that how this ABM works, or the missile hits the target that had been placed or that had been chosen as the set point. So suppose that you're given an ABM or the missile which has a location which to hit at this particular point. So a simple way to do this is to utilize an on-off controller where you will be calculating the distance that this missile has to travel to reach this position and the velocity it can achieve. So you know the distance, and you just you have an on-off controller that stays on during flight and turns off at certain distance so that the rocket falls at the target. But the problem with this type of the system is that you will have to, since you know that you will have to compute the error. Let's say the error is the distance between the missile and the target. So you are going to program the controller in such a manner that it senses the error. So you will be requiring a sensor, for example, the radar. A radar antenna will be sensing the distance, and that distance will be given to the controller or to the system that will be operating the controller and will be generating error. So whenever you are going to have error proportional to the distance between the target and the missile, so the operation of the system will be in a manner in order to operate the controller till the missile reaches the target. So you're talking about on-off controller. So the controller will stay on when there exists an error, or when there exists a distance between the missile and the target. But when the missile reaches the target, in that case the error will turn zero, and in that way you will be having no error generated and the controller will turn off. But in order to have this process operated, the controller, since you talk about the velocity of missile, this missile will be moving with certain velocity. You computed the distance, and the time that it will take will be equal to, so that will be equal to d by v, distance upon velocity. Now, since you know that this particular missile, after you computed the time, you know the distance or the error, which is d, and the velocity of this missile is v. So you programmed the controller, you gave the time to which the controller has to operate, and after this period of time the controller has to turn off. But in doing so, you know that the error is only going to be zero when the missile reaches this range shown by green line. So you're going to get error within this range, otherwise there will always exist error. And thus when the controller is going to turn off when the missile reaches this particular range. So which means that before reaching this particular range or this particular area, the controller will stay on. And since there will be a height that the missile attains from the ground level, say that height is this much, and because of all that acquired momentum, the missile will, instead of hitting the target because of the momentum, it will go far away from the target. So this is something not desired. You want the missile to hit at the specific target. So one way to achieve this is that you program the controller in such a manner that it may stop at certain position somewhere in the middle of the path, somewhere in between the path. So let's say the missile operated, the controller was on till this particular position, and you manipulated the distance that will be required for the missile to hit the target. And say you got this much distance calculated, and so this is a way that you may allow the missile to hit the target by turning off the controller at this particular position, so that post the turning off the controller, you may have momentum which will allow the missile to hit the target. So this is one approach that you can have using on-off controllers. But again, there is a drawback. If suppose that the missile, because of some internal disturbances or changes in the system parameters, or some external disturbance, let's say because of air gust. So what is going to happen is that it might be possible that the missile will take a different direction or it will deviate from its original path. In that case, again, since you don't have any mechanism to bring back the missile back to its exact path or exact location where it would hit the target. So again, you're going to have the path different from the original path or the desired path. And in that case, again, if the missile is going to deviate from its original path, it will hit some other location. So in order to make the rocket not only to fall at its exact target, but also to make it complete its course in a specific time period, we should have controller that firstly moves the rocket at high speed, then when it closes the target, its speed keeps on reducing constantly. So this is similar to the approach you apply brakes while driving when you see a red light ahead. This type of control is possible by using a derivative control on element proportion. So we'll talk about this PID controller later. This is an on-off controller. So there are problems associated with on-off. So in order to overcome this problem, what you do is you will employ controllers based on PID. In fact, the control strategies that are employed in defense are quite sophisticated and advanced. I am talking about PID just to explain you, just to make you understand that how PID operates. So if you're going to incorporate a proportional, so as I told you that PID stands for proportional, integral, and derivative control. So what it means is that you will be having a controller. Let's say we represent the controller by C. Then you have the plant or the process that represent this by P. Then you have the actual output. From this actual output, what you do is you give a feedback. So you have feedback. For this, you might be using sensors like radar antennas. So let's say FB represents the feedback. Then this feedback is given to a comparator or an input here with a plus sign as with the reference input. And then you have this as actual output which the process is achieving. So this generates the error. The output at the comparator side generates the error. And it is this error which operates the controller. So whenever you're going to have finite error, the controller will be operated. Otherwise, the controller will switch off if the error is zero. So in case of proportional, integral, and derivative control type of controller, what you do is you're going to replace the C block. So you are going to have a PID controller in place of the C block. So let's place PID here. So now what you are going to do is you are going to have PID in fact comprised of three controller which we'll discuss tomorrow. We have a proportional controller, an integral controller, and a derivative controller. So they are connected in parallel, and the output from each of these controller will be summed through a summer or an adder manner. So all of them will be having a plus sign, and the error is being provided to each of these blocks separately. Then this will be generating the output of the PID. So this is the output that will be fed to the process or the plant. Now what you're doing in each of these blocks is that you, in case of proportional controller, you're trying to scale up the error. For example, suppose let's say you had a steady value of error of let's say 5 and the value of proportional controller was let's say 2. In that case, you're going to have an output of 10 at the output side of the proportional controller. So what you did is you scaled the error signal by 2. So depending upon what value of P you're going to choose, you are in fact going to scale up or you're going to amplify the error that is fed to the proportional controller. Now, integral controller, what integral controller does is that it keeps on integrating the error signal over a time period. So, and again, that depends upon, it will be accompanying a scaling factor as well, called as Ki. So, you'll be having Ki in the integral controller, the scale factor that is associated with the integral controller, and you're going to integrate the error signal. So, the output of the integral controller would be something like Ki, the scaling factor. You can take it as 1, but it's good to have a certain scaling factor that will decide how how slopey your integrating output should be like. The scaling factor multiplied by the integration of the error signal which is fed to the integral input, and this is integrated over a certain time period, let's say from 0 to t or t1 to t2. So this will be the output of the integral controller. And likewise, you now can figure out what should be the output of the derivative controller. So the derivative output looks something like KD, the scaling factor, KD and d by dt of the error signal which is fed to it. An error signal is of course going to be a signal in time domain. So you have a time domain signal ET. And this is the output from the derivative block. So now what you're doing is using the PID controller, you are going to scale the error using the proportional controller. You're going to integrate it using an integral controller, and you're going to differentiate it using a derivative controller. So they have different ways, different benefits of, you will be having different benefits of doing so. The proportion is going to increase the error, which means that the process which is receiving the signal from PID, what proportional controller is doing to the process is, since proportional controller is scaling the error, and thus this will make the process following the controller to run fast if the output of the proportional controller is high. For example, if you didn't scale 5 two times using proportional controller, in that case 5 was going to be fed to the process, and the rate of operation of the process will be different or will be lesser than the rate when you are going to switch the proportional controller having gain 2 or 3 or 4, which makes the input file large. So if you're going to feed let's say 10 to the process, in that case the process will be operating much faster than 5. So this is the benefit of using a proportional controller. Now if you try to link this with the example that I have just given, so if you're going to employ proportional controller in this particular case, so what now you're doing is you have a distance which is, so you have error proportional to this distance, and using a proportional controller what you do is you are multiplying E with Kp, the proportional constant. This is the output from the proportional block. and this output E times KT will be fed to the process. Now you can easily see that whenever you have larger error, in that case the output will be quite large. And when you have a smaller error, which means that large errors mean that the missile will be at a very far distance from the target. But when the missile closes the target, in that case you're going to have this error is small, and thus the output from the proportional controller will reduce. So in this way, what you do is you are going to make the speed of the missile reduce as the error reduces. But it's not sufficient, because you know that there will be a position where the missile will still have some acquired momentum. So you will always require a force that has to restrict its motion as it closes the target. That is possible using a derivative control, which means that if you want the missile to hit the target, and since as the rocket or the missile closes the target, you want its speed to reduce. And just like as I told you that you're going to apply brakes when you drive a car, or you ride a motorcycle. So whenever you see a red light, you apply brakes. So in a similar fashion, this type of brake or this type of restriction to the motion of the missile is possible using derivative control. So what derivative controller does is it tries to oppose the rate of change of the motion that the missile will be having. So since we see that the rate at which the missile will be closing the target will be quite high, and thus the case will give a rise to larger magnitudes of derivative controller, which will, so the larger the speed of approaching towards the target, larger the speed of the missile approaching towards the target, the larger will be the derivative, the output from the derivative block, which means that it will reduce the speed with with higher rates. So now we conclude that the higher the gain of proportional controller, the faster the error will reduce. That is, the faster the missile will move to its destination. And when the missile enters the desired region, the errors become zero, and that turns off the controller while the rocket falls at a location which is different from the desired location. So we try to choose certain values of gain of the proportional controller and as well as derivative controller in order to make it fall to the target. But now if we talk about another example where, let's say, we have the actual ABM, the anti-ballistic missile. So let's say this is the targeted missile. This one is the targeted missile, and this is the ABM, which is following the moving missile. And let's say this was moving with a velocity u. Now, in order for the ABM to hit this missile, it has to have velocity larger than the velocity of the targeted missile. Now, one way is that if you are, this in fact is not possible using on-off controller, because you will have to continuously follow this particular missile, and for this you will have to generate an error which is proportional to the distance between them. So once the ABM closes the target, in that case the error is going to reduce, and the larger the error, the proportional controller will cause it to move with a larger velocity towards the targeted missile. So this was given by the expression error times Kp. So if you have a larger error, the output from proportional controller will be large, and the speed or the V will be large because of proportional controller. And if this ABM attains the target very closely, and in fact now let's say it is moving with the same velocity as that of the targeted missile. So in that case the error E will be small because they are very close to each other and moving with the same velocity. And moving with same velocity means that the rate of change of error d by dt of E, this will also turn 0, which means the derivative block is going to give 0 as output. And if we see that error is very small, in that case the output from proportional controller will also not be considerable. So we can assume that to be 0 as well for small errors. Now, in this situation, the problems of such type, then you have integral controller which will be playing its role. So what integral controller does is you have ki integral of error. So in some places you will see this written as SKI, where S is in Laplace domain and in fact is the Laplace representation of the integral. So what Ki integral of e dt does is, so when you are going to have a smaller error e, the integral controller is going to sum up or is going to integrate this error over time. And the output from the integral controller will keep on increasing over time, which will make this velocity v of this ABM increase or will have a larger value than u. So in that case, v is going to be larger than u. And thus the ABM will close the target slowly but surely. So because this is possible because of the integral controller. So in that way, you allow the ABM to hit the missile. And now here's another example that I thought to show you people because this was something that my research student, the students from undergraduate did last year. So they employed PID controller, and this setup shows to control a pendulum which employs a motor, a small DC motor connected to the propeller. So the task here was to make this bob or make this pendulum attain a desired angle which was fed to the controller. So we are going to implement a PID controller and we are going to give reference input to this system certain angles, for example 30, 60, 90, minus 30, minus 60, and after providing the angle reference as a reference input to this system, we will look for the actual output. So the complete representation, the waveforms are not given, but to show you the how the system was working. Let's see. So the system started. We have provided input, a reference input, and it started. So it's the PID controller which is going to control the system now. So 10, 20. So I guess 20 degree was given as input, as reference input. Now we are going to change the angle. So now we change the angle to 40 degrees. So any disturbance or any external disturbance that comes over the system, it will be the combination of PID controller which will bring the system to its desired values or angles. Now 50 degree, then back to 30 degree. So what we did was we provided a series of reference inputs with varying angle, and it caused the system to attain those values. This is 10 degree, 60 degree as input, $50. This is 90. Sorry, 80 degree, 50 degree. Sorry, 40. I think 40 degree. 65 degrees, 25 degree, close to 25 degree. So in fact, you can find multiple controllers, multiple applications of PID control. So that depends upon where you are going to employ the control. And one of the topic in order to employ PID properly is PID tuning, which is not part of your syllabus. So if any one of you implement it in your field work or your research work, you can look into the PID tuning later. So this is all for today, and we'll be discussing about the quantitative part of PID tomorrow. So if you have any question, you can ask me. So I have already shown you this system in our previous lecture. So this is a sort of pendulum. A bob is attached with work on a motor, a small motor. The propeller is attached. So let us assume that this is the initial angle or the initial input, and we now feed the system with a input signal, a step signal, which will be larger than this angle. And if we, as I told you before, that whenever you design a controller, your first task is to make that controller stable. So if you are not going to make the controller stable, then you will be having the problem of instability, and the controller will be the output of the plant will be out of bound. So your first task is to make the controller stable. Then we move towards talking about the proper transient response or the steady state response of the system. So that's the next, the second stage. First stage is to make the controller stable. So this example shows that if you're going to have the values of PID coefficients that are randomly chosen or not properly chosen, in that case the system might become unstable. So let's see how the system works when PID coefficients are not properly chosen. So we see here that the oscillations are existing, and now it can be clearly seen that the oscillations are rising. We have a rising oscillations with time. This is all because we didn't choose the value of coefficients of PID properly. The system is unstable, and the oscillations keep on increasing. So now we're using the coefficients of PID properly in order to make the system first stable. So after making the system stable, now we have a problem of choosing properly the PID value. So if you see this figure, we have an initial value. So this is the initial angle, and we fed this with a step input corresponding to this final angle. But we see that there is a large overshoot, then the system comes back to the final angle. And this is because of the reason that the PID coefficients are not properly chosen, and because of the integral controller, the system came back to its the desired value after exhibiting an overshoot for longer period. So this is what we saw in this waveform. So if you see you saw that on employing a integral controller, you might still have oscillations, and the time that this waveform will take is small, it will be large. So we will have an overshoot, but a slower response. Now, if you do not choose proper values of again derivative controller, so in this example, we have initial angle and then we provide a step angle. We see oscillations here. So these oscillations are because of not properly choosing the derivative coefficients. And after a time, we saw that the bob came to an angle which was the final angle or the desired angle after a period of time, because this is because of integral controller. So not properly choosing derivative gives oscillation, while integral plays a role and bring it back to the desired location. So for this type of things, we require tuning. So this is why tuning is important, in order to come up with values of proportional, integral and derivative values, derivative controllers, the coefficients associated with it, so that your plant works properly. So you can find many more examples in books, as well as if you search for them on internet. that employs PID controller, and how they tune PID controller, how they design it first of all, how they make system stable, and how to approach a fine-tuned PID controller. In fact, PID controller, as I told you before, is a controller that is employed in more than 90% of industries today, and that is why it is one of the important controller uh, up to date till today. So if you people have any question, you can ask me.